Okay, yeah, and I'm not going to be able to see questions in the Zoom or in Slack. So if you can just, moderators can ask them in the way, that would be great. Yeah, so I guess I'm really excited to hear today. We had a really good discussion yesterday about what the timing model was. And I think really the center of everything that we do pulsars is the timing model and the parameters in it. And I just want to hopefully be able to get across just how amazing pulsar timing is and the sort of great things that we can do with the data, especially the data from Meerkat here. So just a bit about me. So it's really great to be here today. I'm originally from Canada, actually, and so this is me in Canada before the pandemic, and that's my dad there. So this is snowshoeing, and I was complaining about the weather in Melbourne being cold yesterday, but it was much colder there in Canada. After that, I did my PhD in the US, and then I moved to Sydney to do a postdoc, and now I'm a faculty at Swinburne in Melbourne. And so my research interests are both timing millisecond pulsars to search for gravitational waves is one of my major interests, and also studying fast radio bursts. But we've been having a lot of great project timing millisecond pulsars with the Meerkat telescope as well. So anyways, so I guess really, when we think about pulsar timing, it's such a powerful technique, and really the power of it is that we can account for every rotation of the pulsar over our data sets. And this is very true. This is true for all the millisecond pulsars that we study. But this technique allows us to do is that things that only cause weak Doppler shifts, that is, if you have things that cause the motion of the velocity of the star to change, those can be confidently detected because we can keep track of how those motions affect the phase of the arrival times of the pulsars. So as an example here, I'm just showing you the, we'll get into what these plots mean in a bit. We've seen a few of these before, but this is a plot of the residuals from a very famous millisecond pulsar called B 1937+21. It's the first millisecond pulsar discovered. And this is a data set that started in 1984 and ended in 2018. And these are the residuals here. And we can see that they're very smooth. They're smoothly tracking over this entire data set. And I can tell you that the last observation in 2018 occurred, sorry, we got hundreds, thousands, millions, billions. I have to keep track of that myself. It occurs 674,489,762,880 pulse rotations after the first observation. And we can be certain of that. Just think about that. I can count the rotations of the star between 1984 and now, and I know it's that, and 1984 to 2018, and it's that. And if I had a longer data set, I would be able to keep on counting. This star is spinning, I think, 1.6 or 1.7 milliseconds. I don't know. If there's any pulsar aficionados online who want to correct me there. Anyway, so the amazing thing here now, right, is that because of this, we can do fundamental physics. So we've got these stars spread throughout the galaxy, and we can do all kinds of amazing things with it through the pulsar timing technique. We can search for long frequency gravitational waves. I won't have a lot of time to go into that in this talk, but we could do tests of general relativity, and Federico is going to bring that home later on today. Measure masses of neutron stars, and this is important now because it's nice measuring the mass of something, but we've got this star that is nuclear matter. So we can now understand the physics of nuclear matter in so much more detail. There's all kinds of other interesting astrophysics as well. we've got these massive, enormous magnetic fields, meaning we've got all kinds of interesting fundamental plasma and electrodynamic effects as well. And we can also use them to study the intersonium. So the purpose of this talk is I'm going to talk to you a bit about the methods and practicalities of pulsar timing. So here's another toy model of a neutron star. We've got a neutron star here, and we've got this region around it, which we call the magnetosphere. And the magnetic axis of the star is misaligned with the rotation axis of the star. And we've got accelerating, as Matthew mentioned, we've got accelerating particles in acceleration regions around the neutron star itself. And in those regions, we can, through a few different processes, we can produce coherent radio emission. So the common assumptions about pulsar timing is that the radio emission is anchored to the neutron star. So this means we're measuring the rotation phase. You can imagine if this wasn't the case and the beam was sort of randomly wandering around, that would probably affect our ability to use those clocks. The other assumption is that the radio emission is stable. That the emission, and what we mean here is emission converges to the same profile at each epoch. And while this is the case for most pulsars, there are notable exceptions. And this is particularly the case where we've got relativistic binary pulsars, which are precessing, meaning that their spin axes are precessing over time as there's spin orbit coupling or other relativistic effects. And so that's one thing. The other thing to keep in mind is, I sort of said, oh, there's some process that causes that produces the radio emission. And that process is interesting. For the purpose of pulsar timing, it doesn't actually matter what it is. But all we care about is that it's got some of these assumptions here are true. And then finally, the other case is that many of the signals of interest don't alter the arrival times of the pulses, but don't distort the pulse shape. So that means that we can really sort of distinguish between some of the processes we're interested in and some of the messy magnetospheric stuff here by that. So for most pulsars are quite faint. So for most pulsars observed with most telescopes, individual pulses are indistinguishable from noise. And so that's to increase the timing precision, what we need to do is we need to average many pulses together to achieve a high signal to noise ratio. And this is just what's shown here, that this is the idea of pulsar folding. So the pulsars that we're studying, we're able to we're timing known pulsars. So we have a good model for the pulsars to begin with. It's not the best model, and we're going to refine that in the timing process, but it's good enough for us to be able to produce pulse profiles here. So the idea here is that you get one pulse period, a second pulse period, a third, and so on, and then you add them all up, you average them together, and you finally end up with a pulse profile. So, of course, pulsars themselves they don't necessarily look like a little spike like this. They've all got a variety of pulse shapes. It will depend on the spin properties of the pulsar and viewing angle within the beam. When we think about the lighthouse beam, it's not the same brightness all illuminating the entire beam. There's a very rich variety of probably of sort of intensities across that beam that depends on these things here. For the purposes, again, of pulsar timing, we don't necessarily care. We don't really need to worry about that. And then I guess I'd also say that these are pulse profiles from the Meerkat telescope put together by Rene. SPIWAC in a paper that Renee has just submitted. The other thing to note here is that the narrow pulse profiles provide the highest timing precision. But you can see here that we're a very wide range of shapes. You've got a relatively narrow one here. This profile has two narrow components, a rather fat profile here, and one with multiple components over a large range of pulse phase here. And the different colors here represent the different polarizations of the radiation. And that's interesting in its own right, but not central to what we're going to talk about today. So we got our pulse profiles now. So historically, and I'm sure we talked a bit about PAT yesterday with Aditya, and I think there's going to be a bit more PAT in the exercise after this talk. So what we want to do, of course, is average our data in time and frequency to produce single profiles in minutes to hours and observations. This is what was typically done when we had relatively narrowband instruments. We look at the total intensity, and then we cross-correlate the observations within a standard that's either a smooth standard or an analytically derived standard. And the sort of definitive definition of how this is all done was put in an appendix in this paper here by Joe Taylor, who won the Nobel Prize for the Pulse-Taylor binary pulsar. Again, as we mentioned yesterday, that this assumes that the off-pulse noise is white and the on-pulse noise is also white. So just to give you an example of what this looks like for a very well-timed pulsar, you've got, so this is an observation from the Parkes Rare Telescope taken in 2018. You can see here the observation. The data haven't been de-dispersed, so that's why you're seeing the dispersion sweep here. So when you average together in time and frequency, you get this nice pulse profile here. If you look very carefully, you can see a little bit of a bump there, and that's actually a second component. So this pulsar's got a main pulse and something that's like what we call intervals. And that's seen here in this analytic template that we use. And then what we do is when we shift and scale the template to match the data, to measure the arrival time, you can see here that this is the data itself. This is the template after it's been rotated. And you can see here the residuals. And the residuals look pretty good. They look pretty white. So if I was to make a chi-squared measurement of this, I would get something close to, reduced chi-squared should be close to 1. And what I find is that when I make the measurement in NJD, and this is the measured value, and we have to keep this to high precision because this in fact measurement has a precision of around 30 nanoseconds.
Now, Ryan.
Yeah.
We have a relevant question to this slide.
Yeah.
The question is, the residuals look white, and what does white mean in this context?
Yeah, we'll talk about white and red in a bit. It means that that there is no structure here, that each of the points is independent of the previous point. So what happens is that if I was to see structure in the residuals here that had a big like sort of S-shaped curve here, that would be those would be correlated, because one point would be the value one sort of phase bin would be have a similar value to the next bin, versus here I would say that the values don't correlate, that they're independent. Well, that's a good point. Okay, so we've got our arrival times. Now these are really the currency of our observation of our big project here. So what I want to do is we want to really extract all the possible physics as we possibly can out of them, and want to understand the arrival times in their entirety. And when we do that, we're going to be able to do the best science we can do with them. So, we said we had that arrival time that was around had a 30 nanosecond precision. So light travels like 30 centimeters in 1 nanosecond. So in 30 nanoseconds, you're talking 900 centimeters, right? So it's not 9 meters. And we can get timing precisions much better than that. So we're talking the ability to measure distances to objects that are, thousands of light years away to precisions of, tens of meters or less. So within these uncertainty, within the arrival times, there's the fact that the pulsar is spinning down. The pulsar is losing energy, of course, because of everything that's going of producing all the radiation that it emits. But so that could produce things. We have to be cognizant of the fact that our arrival times might show biases or uncertainties if there's pulse shape variations. We'll get into that in this process, especially called pulse jitter. The exciting things, of course, is we can see the reflex motion of the companion, right? As the star moves further away from us, the arrival times are going to take a bit longer to get to us than if than if it's closer to us. And as there's this binary orbit, that's what happens. We also see the arrival times vary as the pulsar travels around, as the Earth travels around the sun. So of course, if the time of the year where the Earth's orbit makes us closer to the pulsar, then the other time of the year is going to cause large arrival times variations. And that allows us to measure the pulsar's position on the sky and the pulsar's proper motion. We can also potentially sense the fact that the radio waves, as they cross through the solar system, they're not crossing as a plane, but as a curve, because the pulsar is at a finite distance. And that's the effect of parallax. So we can potentially measure the distance. We can measure the distance to pulsars that way. There's gravitational waves as well, potentially. And what they do is they'll distort space-time between us and the pulsar. And that causes, you can think of that as either causing the effective distance between the pulsar and us to change, or the propagation time to change. Finally, we can see the warm electrons in the interstellar medium as well. And this is an effect called dispersion here, which is just shown down here is this line that is has a parabolic curvature. Also, the other important thing is that we have to move to an inertial reference frame when we do our pulsar timing, and that we choose that to be the center of the solar system very center. And where is the center of the solar system, you might ask? But you have to talk to your friends at NASA or another space agency who've modeled the masses and motions of all the planets in the solar system. And it turns out that there's some uncertainty in this, and we're potentially sensitive to that. So as we talked about yesterday, what is this timing model? So after we've discovered a pulsar, we build up a pulsar timing model. And what we'll talk about in a bit is, to test the model, we're going to look at the timing residuals, and we're going to, by comparing the measurable arrival times to the predictions based on this model. What we'll see is that unmodeled or inaccurate parameters in the model lead to structures or excess noise in the residuals that we want to understand and build up a better model. And as I mentioned earlier, we need to transform chimes to the inertial reference frame. So what we're doing is we take our measured arrival times, we correct them to a terrestrial time standard. We account for a dispersive delay, and I've got a sign error here, which should be dm over f squared, not dm divided by f minus 2. And then we've got terms relating to the solar system and terms relating to the binary pulsar. And Federico's going to talk a bit more about especially these terms here. But these term, the most important term here is what we call the Romer delay term, which is basically telling you how to move, transfer depending on where the pulsar is, where the Earth is telling you what time the arrival time should have passed through the solar system, such as the solar system very center. So just to give you an example, again, this is Park's data from a few years ago now. And this data set again is what we call very white. There isn't a lot of structure in them. The arrival times are the residual at one observation and the next observation don't depend on each other. And these are the timing residuals. So this is the difference again between the maximum likelihood model and residuals. So here's the best model for 1999-3744. And here now is a model for the arrival times when I assume the pulsar isn't slowing down all the time. So what you can see here is that if I don't account for that, the arrival times here, which are varying by, have a sort of 100 nanosecond standard deviation, there's, on the order of 100 milliseconds peak to peak variations here. So obviously we have to model that this is part of the model. This is an important part of the model. So, and what that means is that anything that looks like this is going to get absorbed into fitting for the pulsar spin down. As mentioned earlier, that we were able to measure the pulsar's position as well. So again, here's the best model. And here's what happens if I assume that the pulsar is 1 arc-second offset from its actual position. You can see here, this is causing a signal that's 1 millisecond peak to peak. So this is again telling you that how well we can measure the positions of pulsars using the pulsar timing technique. And you can see here also the signature itself, it's got this sinusoid, right? This is a sinusoid and it's got a period of 1 year. And that's just because this is an effect related to the Earth's motion about the sun. Sorry. Now, here's a deterministic contribution. Another one, this is the timing parallax. This is the fact that the pulsar waves as they cross through the solar system are curved. And it again causes a sinusoidal signature, but it's a sinusoid at a period of half of a year. And you can see here it's much smaller effect, but it's still present. So by measuring this, we know that this pulsar is at about 1140 parsecs distance. I didn't do that by just looking at this plot. I knew that before this talk. There's other sort of deterministic effects that we need to account for. Not necessarily astrophysics, but it's instrumentation. So this Parkes data set is comprised of arrival times measured using different systems. We referred to backends yesterday in Marissa's talk. And that's the recording system that actually holds the data. And you can see here an example of a plot on the top, and it looks like there's a bit of a jump here. And then it's a steps change here. And I remember looking at this plot, and then Matthew Bale walked into my office, and this was a while ago. And we looked at this looks funny. And when we went and looked at the sort of observing logs, that at this time, there was a firmware update. So on this MJD 55319.18, there's a change in the way the systems worked. And that change introduces an offset that wasn't accounted for. And accounting for that offset was really important in making sure that this data set was sensitive. And you can imagine these things are quite subtle, but if they're not accounted for, it's challenging. Going back to physics, we saw a version of this plot yesterday. This is again now the spin period and the spin period derivative of the pulsars, right? So this is how fast they're spinning. And this is how quickly that they're slowing down. There's all kinds of different pulsars here. We call these pulsars here either kind of canonical pulsars or normal pulsars. These pulsars here are magnetars, and I won't go into much detail about them because for precision timing, they're kind of useless. And down here is the really exciting bit, right? These are recycled pulsars, right? And lots of them are binary. So there's spinning a lot, spinning quickly, and as Matthew sort of mentioned yesterday, there's this there's a process that the binary evolution has caused them to be spinning so quickly. And they're also, interestingly, they're not the fastest spinning ones are the ones that are the spin rate is slowing down the slowest, if that makes sense. They've got a very small spin derivative. So that's sort of the fundamental properties here, and you can see here how, assuming that the pulsars are losing energy through a dipolar emission, you can estimate the pulsar's age and magnetic field strength based on these two quantities here. And these are lines now of constant age here. So these millisecond pulsars have characteristic ages of billions of years. And they have spin, magnetic field strengths that are relatively weak at 10 to the 9 Gauss. Whereas pulsars up here are very young and have much higher magnetic field strengths. And these are, we think of pulsars up here as being the ones that are formed after supernova explosions. And they sort of, over time, are going to move through here on lines of constant magnetic field strength if their magnetic field's still the same, and then eventually go into the graveyard. Some of them might end up being recycled and come back up here. So for the purposes of a lot of the stuff that we like to do, we're trying to do tests of physics. What we want to do is study pulsars that are either fully recycled or partially recycled. And these are nice because what we can do is through the binaries, these pulsars here have interesting binary companions and interesting binary orbits that we can measure. And these ones here are exceptionally spin stable, so we can use them to search for gravitational waves. And a lot of the times here, these ones here, we can measure Shapiro, what's called the Shapiro delay, which Federico will talk about, where we can measure neutron star masses. So the neutron star, again, has an interesting composition where the outside is made of iron, an atmosphere, and then the interior composition is not fully well known. What if it's deconfined quarks or whatnot? But we can, by measuring the neutron star masses, we can potentially understand that better. We also know is that there's an interesting interaction between the surface, which is again is going to be potentially crystalline, solid, and the interior, which is going to be superfluid. And there's potential interactions between angular momentum transfer between the interior of the neutron star and the surface. And again, remember when we're timing a pulsar, we're timing the surface of the star, not the inside. So glitches are one process that is one of the things that we'll look at in one of the exercises, and it's a sudden change in the pulsar spin. There's spin frequency, firstly, and potentially it's spin frequency derivative. And it's caused, usually it causes an increase in the spin frequency. So pulsars are usually slowing down, so occasionally they spin up a bit. And again, glitches are commonly observed in pulsars, and as I said, caused by this angular momentum transfer between the crust and the core. And if I was to look at a glitch from a pulsar, for example, here in the timing residuals, what I'll see here is that all of a sudden the arrival times start arriving early, right? And that makes sense. If the pulsar is spinning faster than it ought to be, the arrival times will come earlier than we expect. And this is just an example of a few different plots after fitting a few different ways. But the key point here is that you'll have something that looks like this. Okay, so that's sort of where we're at with deterministic terms. So what we mean here is that if the initial state of the system is known exactly, we can a feature can be predicted. And like things like the pulsar binary orbits, it would be that way. If we knew exactly when what the pulsar's state was at the beginning, we'd be able to predict how it goes forever. Of course, there's always this measurement uncertainty, and over time, with more measurements, we can make better models. On the other side of things, there's systems that are stochastic, and this means that the system evolution depends on chance. It depends on random variables. In between, there's things that look stochastic and look random, but are not. So we're going to think a bit more throughout this talk about identifying and assessing and characterizing stochastic or random processes as well. So when we think about these types of processes, we sort of touched on white noise earlier, and we introduced a concept called red noise in the next slide. But this really has to do with power spectral estimation. So oftentimes, when we think about signals in our data, it's easier to think about them in the frequency domain rather than the time domain. For example, when we looked at that sine wave that was caused by the Earth's motion in the pulsar data, it had a very complex signature here, which is also sine. But we know a sine wave can be expressed by three numbers: an amplitude, a frequency, and a phase. And power spectral density allows us to look for signals like that in our data. And we do this through a process called, for example, through a Fourier transform, in which we project our time series onto a set of sinusoids. And then what we do is, instead of looking at the amplitudes of each of the sinusoids, we look at the amplitude and phases of the sinusoids. We look at the power, the amplitude squared in those. That's what we call a power spectrum. And this is useful if we don't care about the phase of the signal, which we often don't care about. So here's just an example of what things look like in different domains. And you can see here just the example of the sine wave, which in the Fourier transform picks up at two different spikes here. So you have to be a bit careful in our pulsar timing, when people, especially like me, will use frequency in different contexts. So we'll think about the radio frequency of the observations, but we also have sort of the fluctuation frequency of these power spectrum here. And sometimes I'll even speak about gravitational wave frequencies. So then here's just an example of what we're just talking about, these different types of noise processes, right? So if I have a process that's white noise, it means it's uncorrelated between different observations. And if I was to take the power spectrum of it, it would be flat. It's got power at all frequencies. If I've got red noise, it means it's correlated between observations. And things like random walks can be this way. And what that means is that there's more power at lower frequencies. It means that if I look at observations spread farther apart in time, well, there's this correlation, there's bigger deviations between them. And that's shown here in this plot of the red power spectrum. And there's things that could be in the middle that are sort of red, but then cut off. So that's just where we talk about red noise versus white noise. And I'll show you examples. We'll see examples of what these look like in time series later on. But it's again useful to model them this way because in this Fourier domain, they're represented by, like a red process is represented by its amplitude and its sort of slope here. Okay, so now we'll just have a bit of a walkthrough about different sorts of white noise processes. Different sorts of noise processes in general. So, while pulse profiles usually average to the same shape, individual pulsars can have different shapes. And this has been known since the beginning of pulsar, beginning of observing pulsars. And here's just an example of a very old plot of a slow pulsar. You can see here that all the individual pulses look different. If I was to observe this pulsar at different epochs, the pulse shape probably converge to the same value. However, the fact that these vary by more than what I expect from just the noise off pulse, the thermal noise from the system, means that there's going to be excess shape variations relative to what I predict based on the noise offset. And this causes pulse shape variations that are uncorrelated from pulse to pulse. Or if not that, have a short correlation time. And when we're talking about timing observations of pulsars, we're talking about campaigns that last years. And so this is a form of a white noise process. So this is also very famously put onto a cover of this album here. And this is observations now from the Arecibo radio telescope. Again, now when we look at the residuals, we can see this effect in timing of high precision timing pulses as well. So again, this is Arecibo observations that I took as part of my PhD thesis. And these are taken in 3 different frequency bands that are relatively close together in time. And you can see here that in this lowest stop band of observations that the error bars here are not are much smaller than, the variations of the arrival times is much bigger than the error bars. And so, as we discussed before, we would have a reduced chi-squared here that is much greater than 1. And this is the effect of pulse jitter here. And so this is how it's manifested in the arrival times. Interestingly, if I was to correlate the arrival times in this band with this band, I would see that they actually go up and down in the same way. And again, that's suggesting that that's a broadband process for this pulse shape variations. So one of the things that we want to do when we do a pulsar timing is account for this in our arrival times. We're going to modify our arrival times to, we'll modify the arrival times, we'll modify the uncertainties in our arrival times to account for this. We're going to increase these uncertainties. So getting back to, again, this plot of the first millisecond pulsar, 37 plus 21. This is similar, if not the same data set. And you can see here this thing here. This is you're seeing gradual variations here with time. You might think at first this is just looking like a perfect cubic, but it's not. This is a red noise process. And we refer to one type of these things as timing noise or spin noise. And again, we've known about these type of things in young pulsars for a long time, where there's excess red noise observed in the residuals of young pulsars. But it's also manifested in millisecond pulsars as well. This process here specifically is achromatic. It's the same in all frequencies. And this is interesting because now this is a process that could be impacts the precision of arrival time measurements, and impacts that could impact our timing analysis. Because it could look like other signals we're going to look for, like gravitational waves, which also affect arrival times in the same way, and potentially a red process. And we also really need to account for this when we're undertaking tests of general relativity and searching for neutron star masses. So just give me an example of other examples of what red noise looks like. So here's just an example of a few plots of the same statistically identical process, but I've just taken different realizations of it, meaning I just started it off with different initial parameters. And it's just different random, it's just different random realizations of the process. So what you'll notice here is that despite having the same statistically some properties, they have a different, the realizations look quite different. And you can see here, this one kind of goes up and down in a way that's almost sinusoidal-like, but not quite. This one's a bit all over the place. this one kind of looks like the, this one looks like the plot in the previous slide, sort of. This one goes the other way, right? So there's, despite these things being statistically identical, they can be manifest different ways, and this is going to complicate the analysis as well. So yeah, just an example that we have some pulsars that were looking pretty white, some that again have a white noise, meaning that these data look pretty uncorrelated. This is very red process. The points here are close to each other, and if I just look at points far apart, we'd expect that the differences to be much larger. So that's one type of red noise. Another type of red noise that's frequency dependent arises from the interstellar medium. And in many of our data sets, this is the largest signature that we will see after we've accounted for all what I call the deterministic terms in the timing model. And this is from the variations in the dispersion measure. So the dispersion measure is telling you about the total column density of electrons on a site. So pulsars are sensitive to the entirety of the ionized interstellar medium along the line of sight. And you can measure the effect of every single electron, which is pretty cool. However, as the pulsar moves through the galaxy, and the Earth orbits around the sun, these lines of sight can change, column densities. And that will cause us to be sensitive. When the column density changes, we can measure that in a data set. The effect is strongest at lowest frequency. So these are data taken at 3 different frequencies with the Parkes radio telescope. And red is the lowest frequency, blue is the highest frequency, and black is in the middle. So it's good cognition there. We've got long wavelength, short wavelength. And you can see here how, for this pulsar, it's got very strong variations in arrival times at low frequencies, and they get smaller as you go to high frequencies, and almost just invisible here. So this is again often is characterized as a red noise process, but fortunately, in the case of this process, because it's wavelength dependent, we can fit in, we can model it and account for it when we in our time model. Okay. So in terms of modeling the noise, what we want to do is we want to model the white noise with parameters. We often call these EFAC and EQuad, and these are terms that that we add to the uncertainties in the TOAs. The red noise we often model as a power spectrum in this spectral modeling process. So we model it as to have, for a fluctuation frequency here, we model it to have an amplitude and a spectral index. And in Bayesian efforts that we can do this, includes in the model. We can also include more complicated models for band limited processes as well. There's other types of noise that people have been adding in to account for things, and you can ask me about that in the Slack if you want to hear a bit more about that. But as our data sets become more complicated, as we do projects that are international, where we combine data from not just Meerkat, but other telescopes as well, things become a bit trickier. Good. Yeah. In addition to that, there's I won't dwell too much on this slide, but there could be other types of noise as well associated with the interstellar medium as well that we need to account for. Okay. So in terms of our model for pulsar timing, we've got arrival times. So we've got a timing model, we've got white noise and red noise that are in our TOAs. The timing model is our deterministic term. So red noise can contain a lot of things. It can contain gravitational waves, hopefully, and then but also spin noise and interstellar medium noise. The white noise contains both the thermal part that we know how to estimate, but also effects of pulse distribution and potentially instrumental effects. So in terms of things, and if we're thinking about fitting and marginalizing the deterministic terms, to do that without too much effort, what we want to do is, if we're interested in finding gravitational waves, we want to minimize the stochastic terms relative to the gravitational waves. Maybe you're not interested in the gravitational waves and you just want to prove Einstein wrong, and then you don't necessarily care about that too much, but you still want to be able to model those stochastic contributions. And we really need to incorporate these contributions into the logarithmic function. So I think at this point, I might suggest that we pause for questions or take a 2-minute break, just so to let people has things to sink in. Myself grab a glass of water in just a second, and then we'll be moving on to more how this all works and how we do this in tempo 2 in a bit.
Okay, thanks, Ryan. So we do have some questions. Early on, you showed a plot of timing residuals. I think it was of, oh, Ryan's gone to get some water, I think.
Yeah, no, come back. I can hear you. I can hear you, don't worry.
So you showed a plot of some timing residuals of 1913. And there's a question, what does the gap at some places in this graph signify?
Which one was it, did you say? This one?
It was a timing residual plot early on, but it was like this one.
I think it was one of the first plots, Ryan, which had gaps in it. Yeah, I mean, even this one has gaps in it.
Yeah, so depending on, these data can be taken with different telescopes. And to get, unfortunately, not everybody thinks that we should be using all the telescopes all the time to do pulsar timing. And telescopes even like Meerkat get used to do other things. And to observe, basically to do these timing campaigns, you have to apply for time for telescopes. And just depending on whether or not the timing campaigns have been going on, you end up with gaps in the data.
Okay, thank you. So you started talking about this, but maybe good to go into a bit more detail.
Mm-hmm.
In the search for gravitational waves using pulsar timing, what kind of perturbation do we expect in the signal of interest, which is the residuals?
Yeah, it's roughly 10 nanoseconds over 5 years. So it's a pretty small signal. The interesting thing about the thing that we expect it to be is a red noise signal as well. And because the signal is bigger at lower frequencies, it means when we have longer data, the amplitude of the signal grows. So if I was to look at this pulsar here and look at a short sample of it, the residuals would be quite small, would be quite low. And if I was to look at a very short signal, it would be a very good pulsar because this is a very bright pulsar. And then residuals would be very small because I'd be fitting the time model would be absorbing all the red noise. The same thing is true with the gravitational wave signal as well. So even though it's 10 nanoseconds in 5 years, I think it goes as t to the 5/3, I think, time. So that you get a significant improvement as you have longer data sets. And now with a lot of projects, we've got data sets that are 15 years or even longer. That being said, at that point I'll keep my Meerkat hat on again, and with Meerkat we can time a lot of millisecond pulsars, so we can potentially detect this signal with a much shorter data set.
Okay, thanks, Ryan. And one more question. When we talk about doing tests of general relativity, do we mean over tightening the constraints already obtained, or are there other tests where we can test general relativity and competing alternative theories of gravity?
I'll encourage you to stick around for Federico's talk, because he's going to go into all those details. It's great having somebody speaking after you, so you can just sort of say, oh, Federico has, so we'll explain it to you. So, well, add a few more things to Federico's talk, but that's going to, yeah, but Federico's going to talk about that. And the answer is yes.
Great. Okay, so did we want to just pause for another couple of minutes? Or, yeah, to resume now.
If people want to put thumbs up or thumbs down in reactions that we have.
Okay, let's just start in a couple of minutes. I might also go and grab some water, and other people can do that if they like.
Daniel, maybe just name a time for people to be back at.
2 minutes. So
on the hour.
Sure.
Okay, I've resumed recording now. So I think, yeah, so Daniel showed a very similar plot, had a similar slide yesterday. And basically, I just wanted to describe a bit about sort of again, remind people about the maximum likelihood versus Bayesian methods for analyzing data sets. So as you mentioned, what we want to do is maximize the probability of this probability here, which is basically looking at the data points, and we evaluate our model at the data points. And of course, if we've got data with different uncertainties, we weight the data differently. So if in maximum likelihood methods that if the parameters are linear, then the problem is linear, and the parameters and uncertainties can be solved using a linear set of equations. And in this case, they're basically, we can fit the model to the data in a single iteration, and there's a unique global minimum, meaning that we know we're at that maximum likelihood. However, if the problem is nonlinear, then it's often possible to linearize the problem without initial parameters. The issue here is that, like things like binary orbits are very nonlinear, in the sense that we can't describe the impact of the binary orbits on the arrival times using a set of linear equations. And we're also not guaranteed to find the global minimum if we do this. So in terms of the maximum likelihood methods, and this is all implemented within many packages, but including something called Tempo2 that we'll go through in a bit. It can often be difficult to quantify the effect of the assumptions and the uncertainties. And as a result, parameter uncertainties can be incorrect, especially when the parameter is detected with low significance. And in the maximum likelihood approaches, it's often difficult to account for the covariance between the deterministic and stochastic processes. However, they're very, very useful if you've got very high significance detection of parameters. You're not going to you're going to have a reasonable control of the bias and confidence in the uncertainties in the parameters as well. And it's often I will see my sort of recipe towards the end of the talk about what approaches, and looking at things using something like Tempo2 is definitely a prerequisite to doing any sort of other Bayesian analysis. So Tempo2 is software that analyzes the arrival times. And what we do is we'll input things like the arrival times. We'll have a thing called a .tim file that I'll show you in a minute. And again, we do extensions in Unix and Linux are arbitrary, but this allows us to call them .tim files just so that we know what we're looking at. And the other input would be an initial timing model, which is a .par file. We also have to account for the solar system ephemeris, and this is done within tempo 2 within the par file. And the output would be typically timing with residuals, the residuals of the difference between the TIM file and the model at the value at the times, and potentially an updated timing model that's been improved. So in terms of the TIM file, the basic format looks something like this, where you have a statement at the top which defines the TOA file format, and this is almost always format 1 now. I think in the 1990s there was different ways to format things, but that's different. Anyways, the first column is typically the file name needs to produce the TOAs, but it can be any text string that you want. The other columns have required information. This column here is now the observing frequency that we observed at in megahertz. Then you have the arrival time in MJD, the uncertainty in microseconds, and then the telescope where we're observing it. So those are the required things that have to be in a TIM file. And if you open it up, you would definitely see all of these things here. However, you can also add a lot of other things as well. And here you have to imagine that this is text that is one line in a TIM file. So things here are extending over many different extending over one line. And these are additional flags. And this is just a way to add additional metadata to the TOAs that if you want to go and analyze them within tempo 2, you can use these flags to, for example, identify data that needs to have an additional instrumental offset on it, for example. So you can see here the regular things that we saw in the last slide, which is the meerkat. And then we have these other parameters here, where -FE stands for front end, which means sort of the telescope receiver that's being used. BE stands for the back end. So this is the meerkat beamformer. Then -F is the full system. So we've got meerkat and then the meerkat beamformer. We've got the bandwidth, the integration time. So the bandwidth and integration time, that's in megahertz, and that's in seconds. The template that is used to the timing here. The goodness of fit and the reduced chi-squared. You can see here this is 1.45, so it's not so great. And then the number of phase bins, 1024, and the number of channels, 1024. But again, these flags are all optional, and the flagging itself will depend on how the TOAs, who produce the TOAs, largely, and what you want to do with it. So then there's the parameter file. So this again contains the models for the arrival times. It contains a model for the pulsar spin, a model for the binary motion if the pulsar is in a binary, and again I'll defer to Federico's talk for that. Model of the interstellar medium, and model of the solar system, which accounts for the pulsar's position, its proper motion and parallax, and a line that specifies what model of the solar system is being used. So here's an example of a parameter file, a par file for a millisecond pulsar that's isolated, so it doesn't have a companion. So you can see here, first of all, it's got one column's got the parameter name, the parameter value, and whether or not the parameter is to be fitted for, and its uncertainty. So you can see here, we've got the pulsar name. This is the first parameter. The right ascension, declination, the position of the pulsar in the sky. The pulsar's spin period, spin frequency, and spin frequency derivative. We don't typically specify things in period and period. We do frequency and frequency derivative, pulsar dispersion measure, the proper motion in right ascension, the proper motion in declination and parallax. And then we have these epochs, right? So we have to specify at what epoch are we measuring the pulsar's spin down, its spin frequency. At what epoch are we measuring its position, because of its position is changing with time. And in fact, if the dispersion measure is changing with time, what epoch specifies a dispersion measure? So you can imagine I could add a parameter here called dm1, which would be the dm. Here's now a couple more things. This is telling me what realization of time I should be using, and it's the 2018 version of the time as specified by the Bureau of Weights and Measures in Paris, France. And the ephemeris I'm using is DE436, which is one of the more modern JPL, Jet Propulsion Laboratory, NASA ephemeruses. So when we run Tempo 2, we usually run it, so we run it from the command line, and a lot of what we do is using the PLK plugin, which is a way to visualize the data. So what you want to do is run tempo2-grplk-f, and for example, and it's a Pulsar file and a routine file. And if I want to run it without fitting for any of these parameters, I also type no fit. Anyways, so when that happens, you'll get a window will appear on your screen, and it'll look something like this. So this PLK in Tempo 2 is a very powerful tool, and that's got a lot of different features in it. And let's just go through a few examples of things here. So on the top here, this is a list of the parameters. You'll notice that these are similar to the ones that in the PAR file. Again, this pulsar has a binary orbit, so there's some parameters related to the binary orbit as well. And you can see here, I've got not only dm, but I've got a dm derivative and dm second derivative as well. So those are all parameters in the PAR file, and if they're flagged red here, that means they're being fitted for. And within this plugin, you can go and click on each of these things and just disable or enable the fitting. So if I wanted to not fit for any of these parameters, I would just go click on each of them, and then the box will turn white like these other ones. If I want to refit the model, I hit this button here, refit. If I'm happy with my PAR file, I'll go and hit here, and then I'll be prompted on the terminal line to output a new PAR file. Similarly, in this plugin, I can delete data points if I've got outliers. So if I've got data points here, like maybe, for example, this one might be badly affected by RFI, and I could, if I was to right-click on the TOA, I would zap it and remove it from the data set. And if I hit new 10, it would get rid of it. There's different plotting options here, so you can plot versus day or other quantities on the x-axis, and plot the pre-fit or post-fit residuals on the y-axis, or any of these other quantities. Other things here, down here is where there's instrumental offsets. So as I mentioned earlier, this is a data set that there are some jumps in it, and that is what these are jumps here. Again, I can click on these and enable or disable fitting for those. And the residuals here, of course, this is the sort of the center of the piece, and probably the most important part. So I was obsessing with telling you about all the buttons to press, but this is the data, right? So if we look at this, we can inspect this to see whether or not if the fitting is good or if the fitting is converged. So we can keep track of the RMS of the residuals here, and keep track of the fitting here. So here's just an example of that same data set, where now I've plotted it versus orbital phase. And you can see here everything's looking pretty flat. Here's an example of what happens is if I've turned off the effect of Shapiro delay, which is one of these fancy, which is the effect of the light from the pulsar traveling through the gravitational potential of its companion. And you can see here this beautiful Shapiro delay curve here. And again, Federico will explain in more detail about why measuring these are so important. Let's look at this data set, which is frequency. You'll notice that most of these data are taken at frequency close to 3100 megahertz. There's a few points at a bit higher frequency. Just as an example here, here's now a meerkat data set of the same pulsar. So I fit for similar parameters here. Sorry, the difference with the meerkat data is that the data are taken, we haven't fully frequency scrunched the data, and the data are taken over a wide band. So I've produced TOAs for 16 subbands across the meerkat L-band system. So you can see here I've got frequency coverage from 900 megahertz to 1.6 gigahertz. So yeah, this PLKs are very in Tempo 2 are both very rich ways to look at both to interact, curate, edit TOAs, and fit your data using maximum likelihood techniques. So there's a lot of things under the hood and a lot of little tricks that you can do that we don't have really time to go into right now. But just a few things is that if you click on the PLK window with your mouse, if you do a left click, you'll get information about the TOA picture of the window. If you do a right click, you'll zap the TOA. There's other commands that I like to use, like if you click on the PLK window and then type Z, you'll get a little box will show up and you can zoom in into different regions to look at the TOAs. If you do capital Z, you'll remove the TOAs from that region, so be careful about that. Next, just refit. So instead of having to hit the refit button, you get refit. And you can zoom in on things. And I'm not quite sure that this one might not be correct. This might be related to another program, so I won't dwell on that too much. Okay, so just very, very quickly, when Daniel talked about Bayesian analysis yesterday, there's these key things here that we want to calculate the probability of a model M given parameters X and data D. What we want to do is measure the posterior probability. To do that, we have the likelihood, the prior, and the evidence. And the likelihood is how well does the data match the parameters in the model. The prior is the expected range of parameters for your expected range for your parameters, and you should choose them to be flat or uniform. But you can also make them visible if you want to. And the evidence is how well the model matches the data. So in the Bayesian analysis, instead of finding the parameters that are most likely, we consider all parameters or sets of parameters of interest. We consider only parameters of interest and marginalize over the rest. And what we do is we get a complete picture of the probability distribution for a given parameter when we really marginalize over them. And we end up with plots of posterior distributions and corner plots, and I think they'll be making one of those in the Tempo-ness tutorial later today. So there's some challenges in this. So for parameter estimation, we want to marginalize over the parameters that you don't care about or care about independently of the project, your current task. So for Gaussian distributions with flat priors, this can be done analytically, which is nice. However, for more complicated ways, you need to be a bit creative and use numerical techniques to sample the posterior distributions. There's various algorithms to do this, including Markov chain Monte Carlo's nested sampling of polychord. And yeah, so marginalization is kind of one of the keys to Bayesian analysis. You integrate over the nuisance parameters, and this allows you to characterize the parameters you're interested in most robustly. So like, if we consider this simple case here, where we've got a two-dimensional probability distribution. So this contour plus is showing you the probability density, posterior probability density, which peaks right here. You can see here that if I only care about B, I integrate it over A to get B. So I go from this distribution here, but I just I add up everything, walk it down here all these times, and then I get a final probability distribution for B. And you can do the same thing the other way, where if I'm interested in A only, I just integrate it along B. So then the evidence is the integral of the likelihood function over the prior, and it can be used to evaluate the relative probabilities of different hypotheses. And this again can be very difficult to calculate for large parameter spaces, but we can get this out of things like temponess as well. And basically, depending on your you calculate these evidences for the different models, and then you compare them, the evidences, and if you look at the difference of the evidences, that can tell you which model you should prefer. And it's similar to the AIC that Daniel talked about yesterday as well. So just another thing, I think we kind of touched on this yesterday, which was testing your data for Gaussianity. And one of the things just to keep in mind is that it's not necessarily true that your likelihood function has this form here. So it could be that the probability densities are not this. And if it breaks down significantly from this, that could be it could bias your results. So you can do various tests to test to see if there's if your time residuals are in fact this. So it's worth kind of just thinking about, but today it hasn't appeared to be a significant issue. So just as an example, we go back to this Pulsar 1937 plus 21, and what I'm showing you here now is data from the data that I showed earlier. But we can look at 3 different data sets. We can look at an IPTA, an international data set, nanograph data set, which is data from Arecibo and Greenbank, and this data set from Parks, which is the same 9 years as the nanograph data set. One of the interesting things here is now I've characterized the amplitude of the spin noise and the spectral index. And you can see here that the nanograph data and the other data sets look somewhat inconsistent. So that's interesting. But this is just showing you a corner plot as well. So I think it's really important to talk about interpreting the results of the time model. So when I say, do the residuals look, first of all, look at the residuals like in PLK and say, do they look weird? Do they have signal trends or time or orbital phase variations? Think about how good the fit is, look at what the RMS is and how good the model is. Think about, are the parameters significant and do their values make sense? Like if you've got a proper motion that's implying a pulsar's velocity of hundreds of thousands of kilometers per second, that's obviously not physical. If you've got parallax that's negative, that's not physical. When I look at, do parameters improve the fit, through things like the reduced chi-squared, the AIC, or do they increase the evidence? And you look at sometimes there's different ways to measure things. Like you can measure the parallax used through the geometric terms that I described here, but you can also measure the parallax for a binary pulsar through the contribution to the binary orbital derivative decay, PB, which is related to the ambulance siren effect. And then obviously you can check to see if your measurements are consistent with other previous measurements. Okay, so just my recipe for precision timing. So I like to start off with the Tempo 2 graphical plugin to inspect the residuals. Again, there's this method that I refer to as the Bayes method, where you remove the low signal to noise ratio arrival times to see what's left. This really helps expose any sort of unmodeled physics in your data or unmodeled systematics in your data. Look at the data, sort by frequency, flag by backend to see if there's any obvious back issues there. Other things you can do is you can average data together in PLK using those different flagging things just to see if there's any low underlying red noise trends that might be hidden by large individual uncertainties. And then I would use maximum likelihood methods to explore the data. What are the important parameters, and then understand what are the likely important noise sources. Then use Bayesian methods to explore the models and how are the parameters covariant and which parameters and models are supported. So that's sort of the way I approach data sets. So just to remind everybody, this is kind of amazing stuff, right? We can measure path lengths differences between us and the pulsars, so like 3 meters. And these pulsars are 3 times 10 to the 19 meters away. Who else can do that? We can use this to search for subtle distortions in space and time between pulsars in the Earth and gravitational waves, right? We can use this to test gravity, look at general relativity. And we can use this to study the equation of state of nuclear matter through neutron star mass measurements. So there's so much amazing fundamental physics that we can do with our data sets and with telescopes like Meerkat. And that's just the top. So there's so much fascinating things about neutron stars themselves. So with that, I'll conclude and take more questions.
Okay, thanks very much, Ryan. So we don't have any questions on the Slack channel just yet. So I'll give someone a chance to ask a question on that channel. So while people are thinking about if they have any questions, so what we'll do now is pick up where we left off yesterday and just finish off the PS archive work that Aditya was leading. So there was one final part to that, which was timing pulse profiles to produce times of arrival. And then we'll have a break and then return with Aditya leading some exercises on timing with Tempo 2 and I think Tempo Nest.
Thanks, Daniel. So should I get started with Pat right away, or there are some questions coming in, so maybe you can...
Yeah, we've got one question now. So how do we study the equation of state using timing? Can you please elaborate?
Yeah, so I'll be very brief. That we've got Federico online as well. So what you can do is you can measure the masses of the neutron stars through some techniques that Federico will talk about later on today. And then you can if you've got a pulsar that is bright in the X-rays, you can try to measure its size using its X-ray observations. So I'll leave it at that and say, go to Federico's talk.
Yes, lots of exciting physics to hear in Federico's talk in a second.
Yes, we'll talk about it in a little bit of detail, so please come.
Great. Okay, so no more questions, but yeah, if you do have any later on, yeah, you can always revisit these Slack channels and ask them whenever you like. So now I'll hand over to Aditya and we'll pick up with that PS Archive tutorial we were working through. So yeah, time to open up your virtual machines again and navigate to the directory you were working in yesterday. Okay, Aditya.
Right, I'll share my screen so that people can know what I'm talking about. Right, can you see my screen?
Yes, we can.
Awesome. Right, I'll just give a minute or so for people to just open up their virtual machines and directories. But for people who have already done that, so in the virtual machine, we are currently in the exercises directory and we cd into, I think, lecture 6, pulsar timing models, and open up the PS archive directory as well. And for the section 6, as you can see on the PDF on the right, we basically are trying to estimate or generate arrival times using this command called pat, which is part of PS archive. So for doing that, you cd into the part 2 directory, and I'll wait here. So if I can get a thumbs up on the Zoom for people who are already here, that'll be good. I see a few hands. All right, I see quite a few people are already here, so that's good. So in this directory, I mean, so what we're trying to do now is to just take a step back from where Ryan started off with tempo 2 and first generate the arrival times, which is going to be in the TIM file that Ryan mentioned, which is what we are going to be using with tempo 2 as well. So for doing that, we use the Pulsar pulse profiles that we have observed with the Meerkat telescope and also a template profile. So in this directory, you should find a file called 0835-4510.std. That is your template profile. So I'm going to give, say, the next 10 minutes for people to work through this exercise. Look at the template profile using the commands that we explored yesterday, psr plot and psr stat, and then try running this pat command. You can skip the psr smooth if you want to. It's not required that you do that for now. You can just jump to the pat command, run this command with the standard and the cleaned archives, which is what is there in the part 2 directory, and look at the output, and we'll get back in like 10 minutes to see, to just walk through the results and then jump to the tempo 2 exercises. So Daniel, I think you can stop the recording for the next 10 minutes and then we'll get back, if that's fine.